Assalamu alaikum wa rahmatullahi wa barakatuh. Uh, Today I will be solving a final previous for thermal system design. Uh, but before I solve, I know this is to get you ready for your midterm, but this final previous, the question I'm going to solve today, it basically covers about 90% of what's coming in your midterm. So you will be ready, and inshallah, next tutorial, I will try to solve either an example that has everything covered that's coming in your midterm, or just try to find a small part that I missed, that 10% that's not covered in today's tutorial. I'll try to cover it next tutorial, inshallah. But let's get right into it. This question is broken down into two parts. For design problem one, you have part one with 75% and part two with 25%, but both of them combined covers 90% of the your midterm. In this question, the way it's phrased is this part is just like this text is just an explanation of sorts of the purpose of your pumping system and whatnot, but it holds zero significance in your solving or method. What is truly important is this part here, this small table. Here it gives you the population in this town, uh, so the amount of heads. The water consumption is 150 liters per head per day. The town council wants the size of the tank to be sufficient for 3 days. The town council requests that the tank be filled within 3 days, so you have filling days during the solar hours, so 6 hours per day. The tank is to be cylindrical and its height to be 8 meters. So you have height of the tank. And in this drawing, it tells you the length of the piping system, the type of pipes, and the form of fittings that you have. And it also specifies where the ground is, which you're going to need later on, but we'll get to that later. But before I continue, if at any point that you are lost or anything, please do not hesitate to ask me any questions. And uh, I cannot stress how vital this PDF file is. The way Omar Zaidan uh, solves and explains the questions in this PDF file is almost perfect. Like I can't figure out a single problem. It explains everything down to a T. And I don't know if Dr. Kama would be fine with it, but try to bring it with you to the midterm and try to solve following these steps. That's how I solved this question, and it was perfect. So we'll start right away using Omar Zaidan's sheet. So what we need to find first, the first two things uh, before that, actually, if you look here on this table, it shows you what you need to find on the right side, and it also shows you the mark, like how the weight of each part. So before even starting, just take a quick look at this table and see what you need to find and how, and like the marking scheme, it doesn't really matter that much because you're gonna need to solve everything either way, but try to see exactly what the question is asking you for. So the first thing they want is to find the diameter of the cylindrical tank. Now, in order for us to do that, uh, we need to look at what is given to us about the tank. The first thing we have is the height of the tank, which is 8 meters. What else do we need? We could also find the volume of the tank. Now it's not given to us, but we can calculate it. Now the volume in meters cubed can be calculated uh, by doing the by it could be calculated by the amount of liters per head per day. So you will do 150 uh, liters per head and day multiplied with 800 heads multiplied with the amount of days, so 3 days, multiplied with 1 meter cubed, 1 meter cubed over 1000 liters to get the proper uh, value that you need it in, the unit, which is meters cubed. So we'll have per head, day, those two will be canceled out. And you have liter with liter. After multiplying everything together, you'll end up with 360 meters cubed. So now you have the volume in the right unit, and you have the diameter, which was given to us. I mean, sorry, you have the height, which was given to us as 8 meters. So the equation for the diameter of the pipe, so the equation for volume goes as such. It is volume equals pi d squared over 4 multiplied with the height. Now we have the height, we have the volume. What we need is the diameter. So just substitute the values. So you have 360 equals pi d squared over 4 multiplied with 8. If you rearrange the equation, you end up with a diameter of 7.57 meters. Now, just doing this, you've secured yourself about 5 marks. Just simple multiplication and division, you secured yourself 5 marks. Now, the next thing they want is to find the volume flow rate. Now, this question, this part of the midterm is extremely important because what we need to find is the Q, the volume flow rate. And the Q will like determine everything we solve afterwards. If the Q is too high, like if you get the Q wrong, almost everything that you solve will be wrong. And I remember in the like before the midterm when I took it, the doctor told us that he will not give us the Q. We'll need to calculate for the Q. But he'll most likely do it the same way as he did in this question. All right, now in this question, he gave us we calculated, sorry, the volume, and we can calculate the time. In the question, he told us that it takes 3 days and it will take 3 days to fill up the tank, and it can only be done during the day, during solar hours, which is 6 hours. So in order for us to find the time to calculate the volume flow rate, what we need to do is 3 days multiplied with 6 hours, but we need to find it with the same units, so days divided by days, multiplied with 3,600 seconds over 1 hour. So multiplying everything together to get the time in seconds gives us 64,800 seconds. Doing so, now we can calculate Q, the equation for it being volume over time. So now we have the volume as 360 meters cubed over 64,800 seconds will give us 5.56 times 10 to the power of negative 3 meters cubed per second. Now you might be confused with the times 10 to the negative 3, but it's fine. It wouldn't make much of a difference whether it's the how small or how big it is. So now we've found the volume, Q, and time. Now the volume, we might need it later, but the Q is the most important thing we need to find. So whether they ask for it in the question or not, you still need to calculate it so you could solve further on, unless he gives you Q, which I doubt. So now what we need to find is the area. The next thing they ask for us is find a suitable size for the piping system. So in order for us to do that, the area of a cylinder is Q over V. But this V is not the volume, which we found already. This V is velocity. Now, we have in the tables here, here in the piping system design tables, we have on page 45 the range in meters per second for the economic velocity range. Now here it shows all the, different types of fluids, but in our question, they told us that the fluid is water. So we'll use the range of 1.4 to 2.8 meters per second. So our proper velocity will be between these two. Now, how do we find the proper velocity? We'll have to use V minimum and V maximum. V minimum being 1.4 meters per second, V maximum being 2.8 meters per second. In doing so, we'll also find two areas, A minimum and A maximum. The equation for A minimum is Q over V maximum, and for A maximum, it's Q over V minimum. Now the Q in both questions remain the same, but just the velocity changes. So A minimum would be 5.56 times 10 to the power of negative 3 over 2.8, giving us an area of 19.86 centimeters squared. And for the A maximum, we use the same Q, but the velocity would be 1.4 meters squared, which will give us an area of 39.71 centimeters squared. Now, why are we finding it in centimeters squared? Because in the tables, you'll see that it's the values for the flow area are in centimeters squared. And that's the best way we could find it. So instead of converting it and like converting every single one, just find the area in centimeters squared or convert it to centimeters squared to get it. Now we have a range of area, A minimum and A maximum. What we need to do is we need to go to table D1 and we need to find a flow area with the same units where it is between these two. So we have 19.86 and 39.71. So these are way too small. We just keep going. Here we go. 21, but this is 30.86. So this is also an option. And we have 47 here, so this is not an option. The one before it is 13. So this is also not an option. The only two we have within range is 2 and 2, 1 over 2. Now, when you're calculating, when you're trying to find a suitable nominal diameter, don't forget to see if the schedule is mentioned. Now here they told us that the pipe is PVC scheduled 40. So when we go to the tables, we will make sure to look at the 40 standard schedule and to get these values. So these we don't care about, nor do we care about these. We only care about the 40 standard. Now in the question, if it's not mentioned, if the schedule is not mentioned, you just assume that it's standard. So now we have these two options. Now, when you have more than one option, make sure that you always choose the bigger one, the one with the bigger area. So we have two options. We have 2 nominal diameter and 2 1 over 2 nominal diameter. Out of these two, this one is bigger, so we would go and calculate using these parameters. Now, we will also need to recalculate the velocity because now we have a new area. So for 2 1 over 2, we have the following dimensions. We have an inside diameter of 6.271 centimeters and an area of 30.89. So ID equals 6.271 centimeters and the outer diameter, the area equals 30.89 centimeters squared. Now, when you get these values, just so it's simpler later on, just convert them to meters. So we'll have 0.06271 meters, and we'll have 0.003089 meters squared. Now we can calculate the new velocity with these new parameters. So V new equals Q over new area, which equals 5.56 so our new velocity would be 1.8 meters per second. Now, what we'll do now is we will go, sorry, what we'll do now is go back to the uh, tasks that we need to find, and we'll see that we found a suitable size for the piping system. Also, we also found a proper velocity of water for the piping system. So that's 5, 8, 5. So that's what the marks that we have so far. Now in this question, now this part, find the total head of the system will take some time to get to, but it won't be hard. We'll just follow the same system that we've been doing so far. Now what we need to find the total head, the change in head, sorry, is we need to find the properties of water, the properties of the pipe, now the properties of the water can be found in this table. If you watch the previous tutorial, you'll see how to read this table, but I'll repeat it again quickly. To find the density, you need to multiply the specific gravity by 1,000. And to find the viscosity, you need to multiply the unit by 10 to the power of 3, the value by 10 to the power of 3. So we'll end up with mu, density equals 1 times 1000 equals 1000 kilograms per meters cubed. And the viscosity would be 0.89 times 10 to the power of negative 3. Now, to find the properties of the pipe, we'll go to table 3.1, and they told us in the question that the pipe is PVC. So when it says that the pipe is PVC, you'll find it here that PVC means that the roughness of the pipe is smooth. We'll come to that later, but for now, just make sure you write it down so that you don't forget. Now, we need to find the friction factor of the system. In order for us to find the friction factor, we need to find Reynolds number, which is calculated as rho VD over mu. Now we have the density, we have the velocity, we have the diameter of the pipe, and we also have the viscosity. So it will be 1000 multiplied with 1.8 multiplied with 6.271 times 10 to the power of negative 2. We're finding it in we need it in meters, not in centimeters, over 0.00089, which will give us a Reynolds number of now in the table we'll need to uh, rewrite this value to be 1.28 times 10 to the power of 4, because that's how it will be shown in the Moody diagram. And since Reynolds number is greater than 2100, uh, we'll need to go to find the friction factor. We'll need to go to the Moody diagram on page 27. So here we have page 27. This is the Moody diagram where we'll be able to find the friction factor on the left here. Now here we have epsilon over d. Now we found epsilon to be the roughness to be smooth. Now with smooth roughness, you'll go to the first line that you see here, the first one. So we have a Reynolds number of 1.28 times, sorry, 1 second, this is supposed to be 6. We found 1.26. So we'll go down here. We have it at 10 to the power of 4. So 1 would be here. 1.26, it will be around here. So we'll just go straight up, which would be around here. It'll give us sorry, it would be around here. No, Oh, I wrote the Reynolds number wrong. The Reynolds number is supposed to be 126829.21, which equals 1.26 times 10 to the power of 5. So 10 to the power of 5, 1.26 is about 1, so it should be around halfway through here. So if we go up, it'll be around here. If you go straight left, it should be around here. Excuse the bad line. It should give us a friction factor of 0.017. So now what we need to find is we need to find a few other parameters before we can calculate for the head. We need to calculate the length and the summation of K. Now to find the length, we'll go to the drawing provided for us. Now we'll calculate everything, regardless of whether it's going upwards, downwards, left, right, we'll calculate everything. So for the length, we have 40 plus 55 plus 50 plus 8. So 40 plus 55 plus 50 plus 8, which will give us a length of 153 meters. Now to find the values, the summation of K, you come over here and you'll see that all the fittings are regular and glued. So, and you'll see that there's gonna be a check valve, and we'll go to the piping, the summation of K table, which is here, the loss coefficient for pipe fittings. And we'll write it, we'll see what we have and what we don't have. We'll have, we were told that, uh, just give me a second. There's a basket strainer at the inlet. So when we'll need to use this K, we have a, we have 1, 2, and 3 90-degree elbows. And we have a check valve right here. And we also have an outlet right here. So the summation of loss coefficient would be K, the K value for basket strainer, plus 3 90-degree elbows, plus the K value for a check valve, plus the K value for an outlet. Or it could also be written as exit. Both of them work. So the K value for a basket strainer is 1.3 plus 3 times 90-degree elbow. They told us that it is glued. So we'll use the K value for 0.23. Sorry, 0.31 plus a check valve In the question, they told us the check valve is ball. So we will use this one, which is 70, plus an outlet, which is always 1, which will give us the summation of loss coefficient would end up being 73.23. This value does not have any units. So now we will use the main equation, which is the modified Bernoulli's equation, which is P1 GC over rho G So this is our entire equation that we need now, but now we will simplify it. So because we're using metric units like meters and centimeters, we don't need to use GC. So we could ignore it. So we could cancel it out. Uh, the pressure difference between the two has not been mentioned, nor did they ask us to find the pressure difference, so we could cancel these two. The velocity throughout the system does not change, so we can cancel these two. And so what we'll end up with is Z1 now we will take these last two terms and we will make them as a common equation and we will write it as so this is the equation that we're gonna work with. Now regarding Z1 and Z2, it is your choice on whether on what to take as the ground level and what to take as the second level. So some people they prefer to take the ground, this level here, the ground, as the intermediate. So Z1 would be negative 40 since it's going downwards, and Z2 would end up being 50. Or you could take it as this part being Z1, which is 0, Z1 equals 0, and then you'll have Z2 go all the way up, which is 90 if you add the 50 and the 40. Now, I prefer to do it uh, from having this one as Z1 because having Z1 as 0 will end up being helpful later on. So we'll write it as Z1 equals 0 and Z2 equals 90 meters. So we're taking the pump location as the starting point. So we will rearrange this equation to find delta H. So it will end up being delta H equals Z2 minus Z1 plus and since we took Z1 as 0, we can cancel this out. And so we could put the values in. So Z2, 90. plus 0.017 for the friction coefficient, L being 153 meters. The diameter of the pipe, not the tank, is in meters. So now we can easily calculate the value for the head, which is 108.93 meters. That is the unit for the delta H, meters. But we will rewrite, oh, sorry. Before we move on, we'll go back to this table for the marking criteria, and we've calculated the delta H now. So that is 15 points, 15 marks, sorry. Develop an equation of the system curve. This one is also simple. All we will need to do is take the delta H we just calculated, right? But rearrange the equation to be, we'll write this equation. Delta H equals delta Z plus BQ squared. Now we have delta H, we have delta Z, and we have Q. What we need to find is B. So what we'll do is we'll write it out as 108.93 for delta H equals 90 meters for delta Z plus B multiplied with 5.56 times 10 to the power of negative 3 for squared for the value of Q. We'll just rearrange the equation to find the value of B, which is 612,351.85. Now that is not the answer to the question. Once you find the value for B, you need to rewrite this equation. You'll need to rewrite this equation, but this time you're going to keep delta H as delta H, and you're going to keep Q squared as Q squared. So it'll end up being delta H equals 90 plus 612,351.85 Q squared. That is your answer. So now we just got another 6 marks. Check if any excessive vibrations may occur in the system. Now to calculate for vibration, you'll need to calculate for the pressure. In order to calculate for the pressure, you're going to use this equation. Delta P equals 1000 multiplied with the friction over D multiplied with the density times velocity squared over 2. So delta P would end up being 439,164.41 Pascal, which is 439.16 kilopascal. Now, why we want the value to be in kilopascal? Because there will be excessive vibration if the value of delta P is greater than 679 kilopascal then there will be excessive vibration. But since our value is less than 679, no excessive vibration. There will not be any excessive vibration. So now we got another 8 marks. So now estimate the required power of the electrical motor in kilowatts. Consider the efficiency of the pump is 80%. Now, they told us that the expected efficiency is 80%, which is 0.8. What we need to do is write down this equation. Now you don't have to worry, you don't need to do any derivatives or anything of the sort because we can cancel GC out and we have the density, the flow rate, the volume flow rate, the gravity, and the delta H. So we'll rewrite it and we'll make it as to find the power as after multiplying all of them together, we'll have a power of 5941.43. But they told us to find the expected power. So we'll take this and we will write it as so. So to find the expected power, the equation for it is dWA over dt, which equals dW over dt over the expected efficiency. So it will end up being, since we have the value for this part, it will end up being, and since they gave us the expected efficiency of 0.8 or 80%, we'll end up having 7,426.79 watts, but they told us to find it in kilowatts, so it will be 7.42 kilowatts. So that's another 8 marks. If solar panels made of high quality silicon cells are available in the market with a wattage of 300 watts, how many panels are required to power the system? Now, this is a simple question. Ignore all this extra detail. What you need to focus on is the amount of wattage and the question itself. How many panels are required to power the system? Now, we calculated how many watts we needed, correct? So what we'll end up doing is simply taking the amount of wattage we have that we calculated, which is 7,426.79 over the amount of wattage they gave us, which is 300, which is 24.76 solar panels. But we can't have a decimal for a solar panel, so we'll round it up to 25. So that's another 5 marks. Now this question, I doubt that he'll give you this question in the midterm because it's hard to access a link. I'm guessing this previous final is from the time of when it was online, but just to play it safe, I'll solve this for you. It says that this company produces solar pumping system. Which model of their production would you select for this system according to your Q and delta H? So if we go to the website, we'll go to the uh, pump, the different solar pump prices. Now, since they have the pump head, we don't care about the price. He didn't ask us for the price. Like he didn't give us a range for prices, nor did he give us like a specific amount of horsepower. He just asked us with our Q and delta H. We'll keep going until we find a pump that is suitable with our pump head. Now we calculated our pump head to be 108. So all of these are less than 108. This is close, but it's not reaching the minimum of 108 that we need, except for the last one, which is 10 horsepower solar pump with 10,000 watts. So that is the answer that you'll give him. 10 horsepower solar pump, 10,000 watts. That's it. And that's an easy 10 mark. Now for this question, uh, for this part, now we finished the first part. Now we'll just do this second part, which is which will explain, and I'll try to explain to you the concept of cavitation. In this question, for this system shown on figure 2, find the maximum height Z2 where the pump can be mounted without cavitation. Consider the specifications and parameters in the table below and take atmospheric pressure as 101.325 kilopascal. Now, if you go to Omar Zaidan's equation sheet, you'll see this is the this is the equation for cavitation. All right, and in the question, they gave us the length. So we have the length. They gave us the loss coefficient. They gave us K. They gave us the friction factor. They gave us the diameter. They gave us the velocity. Now they gave us the vapor pressure, PV, and they gave us the net pressure suction head required. So this is the equation that we'll end up using. Now both of them are the same. If you look, both of them are almost identical, right? Now the reason for these two different equations is if you're calculating for the equation and you find that the net pressure suction head is greater than the net pressure suction head required, then cavitation will not occur, right? So you will need both of them. But in this question, they told you to find the delta Z, which is this part here. Now, since they didn't give us the value for Z1, we are to assume that Z1 equals 0. And so all we need to find is Z2. Now, if you notice in this equation, they're giving you LS and Ks. Now the S stands for suction because when you're calculating for cavitation, you don't care about anything after the pump, right? All you care about is the piping system from the beginning until it reaches the pump. Now, if you look at the previous question, the piping system starts from the pump, right? This is the pump and it starts from here. So cavitation will not occur in this entire system, right? But for example, if there was a piping system before it, let's say, right? Then there is a possibility for cavitation to occur. That's why in this question he did not ask you to find cavitation. Now, how do we find cavitation? We'll go to, let's find some space to write on. Now, the equation for net pressure suction head required is P1 minus vapor pressure over density times gravity, Z plus Z1 minus Z2 minus friction multiplied with suction length over diameter, suction summation of K plus 1 V squared over 2G. So all we need to do is substitute these values for the numbers they gave us, right? So they gave us the net pressure suction head required. P1 is the atmospheric pressure minus PV 4.7 over 1000 times gravity. Now Z1 will assume it to be 0 since it wasn't mentioned. So Z1 equals 0 minus Z2, which is what we need to find. The friction factor is 0.0015. The length is 20 meters. The diameter is 0.2006 plus the summation of K that they gave us was 13 plus 1. The velocity was 1.8 meter squared times 2, 9.81. So when you have a question similar to this, I highly advise you to break it down, like calculate small parts of it here and there before you start rearranging to make things a lot simpler. So we have 3 multiplied with 9.871 times 10 to the power of negative 3 minus Z2 minus, sorry, I forgot to write the minus here. There's a minus here. Multiply minus, sorry, 14.15 multiplied with 0.165. This is the value for the velocity we had earlier. Let me just specify that for anyone that wants to watch this later. So this is this, and this part is this. So now we could rearrange the equation a little, so we'll end up having minus Z2 equals minus 5.324 meters, but we could get rid of the minuses, so we'll end up having Z2 equals 5.324 meters. Now, after you write this, wouldn't hurt to specify that the pump must not be placed uh higher than, oh sorry, the pump must be placed 5.324 meters away. Just simplifying this to avoid cavitation. Just simply writing this will ensure that you show the doctor that you actually understand the question, and it will secure the marks for you. But even if you don't write it down, maximum you'll lose is like possibly half a mark, maybe one. But that is the question they asked for in this question. And so this is the previous that I ended up that I have ready for this tutorial. Now, does anyone have any questions?
Assalamu alaikum. I do have a question.
Go ahead.
Um, can you just repeat why did we use the equation NPSHR, not the other one, the both equation which are similar?
Because that's the given NPSHR. They gave it to us, the required net pressure suction head. Now, if they told us to in the question, like a different question, if they told us to calculate the net positive suction head, then we'll end up using this equation. تمام. But either way, يعني, as you could see, they're both the same equation.
All right.
The only thing that actually matters is the subscript, whether you use A or whether you use R. That's the only thing that's different and the one that matters. So if you're calculating the initial net positive suction head, then make sure you write the A. But if they gave you the A and they told you to find the delta Z, let's say, or the length, whatever, then use R. Was that clear, or do you want me to rephrase?
Yeah, yeah, understood.
تمام. Any other questions? تمام. So this is the previous that I solved, and as I told you earlier, it's for a final, but the things that we covered is about 90% the stuff that's gonna come in your midterm. The other 10%, inshallah, I'll do it next tutorial. I just need to find a proper previous for the midterm. Now, if any of you have a midterm previous, send it my way, and inshallah I'll solve it and I'll have it ready for our Tuesday's lecture. Inshallah, I'll have the lecture on Tuesday. What time would be suitable? It doesn't matter. We'll talk about this on WhatsApp or on MS Teams later on. But that is all that I have for you today. Any questions? Sorry. Okay, one sec.
Thank you very much.
Oh, what should you print for the midterm? Okay, this table. Sorry, not that this is the question. This table, you need to print this table out. You will not be able to solve anything if you do not have this table printed out. Now, Dr. Kamil, he gave you the this table on Blackboard. Please make sure that you print it out. And when you're solving questions, when you're practicing, or when you're doing homeworks, quizzes, whatever, make sure that you use the physical copy. Don't use your iPads or your laptops, because in the midterm, you'll only have a physical copy. And every single one that I took this course with had the same problem of navigating through this booklet. As you can see, it's 69 pages, and you end up using this booklet for your midterm and your final, and you use it throughout the entire semester. So please make sure you print it out and study for the midterm using a physical copy. The second tutorial, inshallah, will be on Tuesday, just the day just before your midterm. And I'll try to solve another proper previous. If any of you, as I said, if any of you have a proper midterm previous, just send it my way. And another thing you should print out is Omar Zaidan's design problem paper. It's like 5 pages. Print it out, and you could use it as like a guide to help you throughout the solving process. Any other question?